Today's topic is about potential energy of a dipole in an external field. So totally we are considering three cases, and this is the third case, potential energy in an external field. In that third case, potential energy of a dipole in an external field. So we are dealing with dipole. So here we have dipole plus q minus q, and from minus q to plus q the dipole moment acts. Okay, and you have a uniform electric field, and this electric field is due to some other sources, not because of this. So it is uniform electric field. So the uniform electric field goes in this direction throughout. Okay, so what are the points we have to consider now? First point, in a uniform electric field, so now we are considering only uniform electric field, the dipole experiences no net force. So the net force is zero. It does not experience no net force, but experiences a torque, but it will experience a rotational torque. So the torque is given by P vector cross product with E vector. Now what is P vector? P vector is nothing but dipole moment. The unit is Coulomb meter, and cross product with electric field. So if you want to take the magnitude, it will be magnitude of P, magnitude of E multiplied by sin theta. Okay. Now the work done is stored as potential energy of the system. So the total work done is stored as potential energy of the system. If I say system, means it is in between the two charges. Okay, the two charges in an external field is called the system now. Okay, so now we have explained everything. So we have plus q minus q. This is in uniform electric field. So we have a dipole, and it is the dipole moment is directed towards minus q to plus q, and we have P vector, and the angle is theta, a cos theta. So for the adjacent side it is a cos theta. Equivalent moment it will experience in the opposite direction, which is minus a cos theta, and the field is everywhere directed from left to right. So and the distance between the dipole is 2a. So keeping this in mind, now we try to move this dipole from theta naught to theta 1, that is infinitesimally small angle, very small angle. So if you consider for the entire rotation, then you have to integrate, okay, for the entire rotation. But now we are considering only from theta naught to theta 1. So in between we are integrating, here we are finding out the total work done. So work done is theta naught to theta 1, torque, we are finding the torque due to externally applied electric field, which is uniform. It's a function of theta into d theta. Okay, now torque, we know torque is nothing but P and E cross product. So we have magnitude of P, magnitude of E, and sin theta into d theta. So one important thing, if you observe here, the torque produced at, since you have sin theta at 0, sin 0 is 0, and at 180, sin 180 is 0. So in those two cases, the torque produced will be 0, because both are equal and opposite. So P sin theta into d theta. Now P is constant because electric field is constant, uniform electric field, we already told that. And P is also, dipole moment is also constant. Then if you integrate sin theta, you will get minus cos theta. Upper limit is theta 1, lower limit is theta naught. So minus, you pull it outside, minus PE. You substitute the upper limit, cos theta 1 minus cos theta naught. That is upper limit minus lower limit. Now you bring this minus sign inside, you will get PE into cos theta naught minus cos theta 1. So this will be the total work done between the points theta 1 to theta naught to theta 1, and it is stored as potential energy of the system. Now if you are interested between any two angles, you can substitute the value for initial angle, and you can substitute the angle for final angle. If you substitute, you will get a value that is multiplied by uniform electric field and the dipole moment. Then you can find the total work done by the dipole due to external field. Okay, and that work done is stored as potential energy of the system. And I told you, if I say a system, it is nothing but two charges, two dipole plus q1 minus q, a dipole in a uniform electric field. So what is the work done? And also I told you what happens in uniform electric field. This is most important point. Uniform electric field, no net force, but it experiences only a rotational torque. That's why we always deal with torque in the case of uniform electric field in a dipole setup. Okay, that's all about potential energy of a dipole in an external field. Thank you. Nandri.